Welcome. My name is Kevin Joback. I am president of Molecular Knowledge Systems. In this presentation, I will very briefly demonstrate the use of our new modeling document, our machine learning toolbox. Molecular Knowledge Systems provides two main software products. Cranium is our physical property estimation software, and Synapse is our chemical product design software. Cranium's main goal is to provide estimates for the physical properties of chemicals and mixtures. Given only a chemical's molecular structure or a mixture's composition, Cranium can estimate the values of more than 30 physical properties. Synapse's main goal is to use physical property estimation techniques to design new chemical products. Given a set of constraints on physical properties, Synapse will construct tens of thousands of candidate chemical structures, or candidate mixtures, estimating the properties of each one to find those that possess the physical properties that satisfy these constraints. Notice that each product needs physical property estimation techniques. Cranium uses estimation techniques to predict the values of physical properties. Synapse uses estimation techniques to design chemicals and mixtures. Estimation techniques are the key to relating structure to properties and properties to structure. Cranium and Synapse specifically use 4 types of estimation techniques: group contribution techniques, parameter-based techniques, equation-based techniques, and mixture techniques. Both products contain several hundred estimation techniques, but what if no techniques are available or applicable for your specific type of chemical or mixture? Now, with the introduction of our new modeling document, if you have some data, you can now create your own estimation techniques. We will begin our demonstration by obtaining new coefficients for a parameter-based estimation technique. A parameter-based estimation technique typically uses a model that depends upon one or more parameters that have been regressed from data. For example, the technique MKS equation 19, shown here, estimates the liquid vapor pressure as a function of temperature. The equation requires 4 parameters: A, B, C, and D. Given physical property data, we can determine these parameters by multiple linear regression. For example, the squares in the graph represent vapor pressure data for geraniol, a common fragrance chemical. These data have been regressed to give these 4 parameters. The green diamonds represent the result of this regression. The estimates are in very good agreement with the data. I will now demonstrate how to obtain these parameters using a modeling document. The MKS Modeling Examples document is available in both the professional and basic editions of Cranium and Synapse. In this demonstration, I will be using the professional edition of Cranium. I will also be using the MKS Examples Knowledge Base. Both of these documents come with the basic and professional editions. In the modeling document, we switch to the Multiple Regressions chapter and navigate to our example multiple regression. To save time for this demonstration, I have already entered some of the regression's information. Specifically, the knowledge base we will use to obtain physical property values, that the regression is for a chemical, and specifically for the chemical geraniol. I have also entered compilation code. Compilation code tells the regression what data should be compiled from the knowledge base and how that data should be transformed for regression. Once we have specified our input values, we ask Cranium to compile regression values. For this regression, Cranium has compiled a transformed vapor pressure, the natural log of the vapor pressure, and various transformations of the temperature, specifically the temperature itself and the reciprocal temperature. Now that we have compiled our regression values, we can perform our regression. Cranium regressed the coefficients for each of the entered x variables and displays the values and their confidence intervals here, as well as a summary of the regression results below. Now that we have obtained a new set of parameters, we need to add them back to our knowledge base. Specifically, we want to add them back to MKS equation 19. From our modeling document, we execute the transfer values command. And see that our newly regressed values have been added to our knowledge base document. Now we would like to use these new parameters. Change back to the chemicals chapter and navigate to geraniol. Scroll down to the temperature-dependent properties section and select vapor pressure estimates. And we request Cranium to estimate vapor pressures over a series of temperatures using equation 19 and our newly regressed parameters, generating our estimates, once again we see that our estimated values, the green diamonds, are in good agreement with literature values, the blue squares. Group contribution techniques are another type of estimation technique used by Cranium and Synapse. To estimate the physical property of a chemical using a group contribution technique, the software dissects the chemical's molecular structure into a set of groups, compiles contributions for each of these groups, and inserts these contributions into a model. Finally, it generates an estimate. Group contribution techniques are a very powerful class of estimation techniques. However, if we don't have a contribution for a particular group, then we can't use the technique. Fortunately, now with our modeling documents, if we have some data, we can regress values for missing group contributions. For example, if we add a new chemical, whose molecular structure contains silicon, and try to estimate its boiling point using Jobac's method, Cranium tells us that it cannot generate an estimate because the molecular structure could not be completely dissected into groups. If we navigate to Jobac's boiling point technique, we see that Cranium could not generate an estimate because none of the groups used in Jobac's estimation method contain a silicon atom. Since we have some data on the boiling point of silicon-containing chemicals, we can use our modeling capabilities to add such a group contribution. In the modeling document, we switch to the Technique Regressions chapter and navigate to our example technique regression. Again, to save time, I have already entered some of the regression's information, specifically the knowledge base, that the regression is for a set of chemicals, and specifically a set of 20 silicon-containing chemicals. Again, the compilation code entered here tells the regression what data should be compiled from the knowledge base. Once we have specified our input values, we ask Cranium to compile regression values. Cranium notifies us that some of the chemicals did not have the requested property value. For the remainder of the input chemicals, Cranium has compiled their boiling points. Unlike the multiple regression example that we demonstrated previously, no X variables have been compiled. These X variables are entered in the Technique Variables section table. Click on the Sections table, edit the first row, and enter information about the group contribution we want to determine. We enter the estimation technique. We enter the new group we would like to determine a contribution for, a regression variable, an initial guess for our contribution, and a reference and some comments. Now that we have compiled our regression values and specified our technique variables, which are our X variables, we can perform our regression. Our modeling document uses a multidimensional, nonlinear regression procedure to determine the optimal value for our new group contribution. Once the regression is completed, Cranium displays the new group contributions value here and a summary of the regression results below. Now that we have a new group contribution, we need to add it back to our knowledge base. Specifically, we need to add it to Jobac's method for the normal boiling point. We execute the transfer values command. And see that our newly regressed group contribution value has been added to the technique. Now if we return to the chemicals chapter and retry the estimate of the normal boiling point for a new chemical, we see that it obtains an estimate using the value for our new group contribution. Thank you very much for watching this video. Please contact us if you would like more information about Cranium and Synapse's machine learning capabilities, or would like a personal demonstration, or, as always, if you have any questions about physical properties or physical property estimation techniques. Thank you.